Okay, let me write down the alternative Feynman rules that I just mentioned in the previous slide. In momentum space, given any diagram, label all momenta independently without worrying about momentum conservation at vertices. And then for each propagator, write 1 over I delta tilde. Then for each internal momentum, introduce an integral over that momentum, integral dk by 2 pi to the power d. And then number 3, vertex, for each vertex, write I times g. Earlier in the previous rule, that was all, but now in this case, since we have introduced momentum integral, internal momentum integrals, we have to introduce the delta function. So that is 2 pi to the power d delta L of p comma k, where L is a linear combination of external and internal momenta that must vanish due to the momentum conservation. So this is a linear combination of external and internal momenta that must vanish due to momentum conservation. So so L is that linear function, and P is P denotes the set of all external momenta, K denotes the set of all internal momenta. That's a notation, okay? And then finally multiply by 1 over s only. In the previous rule, we had also a factor of 2 pi to the power d times delta function of sum over all external momenta. That is the overall delta function. But we have seen in the previous example, previous calculation that that when we impose all the momentum conservation at each vertices, then that's equivalent to that gives rise to the overall momentum conservation. Let's have a look at that again here. For example, look at this diagram. You see this imposing momentum conservation at these two vertices. We have got these two momenta labeled as P1 plus P2 and P3 plus P4. Now the momentum that is going into that loop should come out entirely. So that is why we know that P1 plus P2 must be same as negative of P3 plus P4. So that is the overall momentum conservation. But that fact that, so we were putting that by hand in that previous set of Feynman rules. but that is guaranteed, that actually follows here from the momentum conservation at these two vertices. If we impose momentum conservation as these two vertices, then the net momentum going into the loop will be the net momentum coming out of the loop. So if you impose momentum conservation at each vertex, then for each loop this will happen. And if there are multiple loops, so the entire diagram, whatever there is there inside, this condition will be satisfied loop by loop basis. And basically what it means is that all the momentum conserving vertices will produce automatically the overall momentum conservation. So that is the case here. In this case, in this when you write down Feynman rules in this way, and therefore you do not have to have that extra conservation equation. So let us demonstrate this with the same example here, but now using this Feynman rule. So this is P1, P2, P3, and P4. And these are the external momenta. They are labeled in the same way as earlier. But for the internal momenta, introduce new arbitrary momenta for each momentum for each line, K1, K2, K3, and K4. Okay, so there are 4 internal lines. And let us now write down the mathematical expression following the rules that I just mentioned here. 1/s is the symmetry factor, and then for the external momenta, I'm supposed to get, as I explained earlier, a factor of capital P involving the external momenta. And then we are left with internal momenta, and we have to introduce this integral. For each internal momentum, use introduce this integral. And then for each internal momentum, just like we have an integral, we have a propagator as well. So there will be a p factor involving internal momenta. And now I have to put the vertex factors for ig. Since there are 4 vertices, there will be ig to the power 4. And now momentum conserving delta functions. So let me count them like 1, 2, 3, and 4, and write down that linear functions inside the delta function. So for the first vertex, it will be P1 and P2 incoming and K1 outgoing. Then for the second vertex, K1 and K3 incoming, K2 outgoing. Then here K2 incoming, for the third vertex, K2 incoming, K3 and K4 outgoing. And the last vertex, fourth vertex, we have K4 and P4 incoming. All of them are incoming. So K4 plus P3 plus P4. Now you see the internal momenta that are not involved in a loop are necessarily fixed by the external lines, external momenta. For example, here in this case, these are K1 and K4. They are not part of loops, and they will be fixed by the external momenta. And these are these two momentum conserving delta functions, these two vertex factors. And therefore K1, let me first eliminate K1 and K4 this way. So it is 1/s P1 to P4. So K1 integral will be removed, and these two delta functions will be used. I will be left with dk2 over 2 pi to the power d, dk3 over 2 pi to the power d. And then K1 is same as P1 plus P2. K2 is so far free, K3 is also free, and K4 is minus P3 minus P4 from this delta function. But this function is same because it's a propagator which is even in P, so that is P3 plus P4 is also right. Then will be left with 2 pi to the power d delta function. I'm this, so I've used these two delta functions. I will be writing these two factors now. So K1 is P1 plus P2. Then K3 is K3 minus K2. This is, both of them are free, and 2 pi to the power d delta K2 minus K3 minus K4. Minus K4 is same as P3 plus P4. So you see here both the same combination of K2 and K3 appear here up to a sign, which means that combination, these two delta functions, if you consider both the delta functions, they don't give two independent constraints on K, and therefore you can just eliminate, say we can eliminate K2 and keep K3. So I eliminate K2 from here. So, and K3 I rename by L. Okay. Then P1 plus P2. K2 is same as K2 is same as P1 plus P2 plus L. Then K3 is L and P3 plus P4. And this delta function is gone, so 2 pi to the power d. If you write the same form of K2 here, P1 plus P2 plus K3, that will cancel minus K3, and therefore it is independent of internal momenta. And what you have is delta P1 to P4. So if you compare with the result that we previously got using a different set of Feynman rules, it's the same result here, and it is just a demonstration of how these new Feynman rules work. One take-home message is that application of all the linear combinations of linear functions of the external and internal momenta gives you the overall conservation of the external momenta, which is independent of internal momenta. So total number of equations, independent equations, those which fix internal momenta, is one less than the number of such equations, number of vertices that we have, right? So this is crucial for the analysis that we are going to do next. Now, so far we have spelled out everything, at least whatever we have to say about the Feynman diagrams at a preliminary level. You may call it a phase 1 of diagrammatic analysis. We are now going into the phase 2 and have better, deeper understanding of quantum field theory using these methods. The first one that we're going to look at is the following. So far, whenever we are calculating, say, gn or generating functional, you have to classify topologically various diagrams, and the method of classification and the parameter that restricts the topological variations is the number of vertices. How many vertices? So you can classify. We have been classifying diagrams in terms of number of vertices. For example, this has 4 vertices. So we ask the question, if we calculate G4, then what are the diagrams that arise at 4 vertex level, which is basically the power of G. So we were counting, we were classifying diagrams as powers of G. Now, if you recall that we had set h bar to 1, and then if we recover h bar, you could ask a question. That's another parameter. Is it related? Is the parameter, is h bar related to some topological characteristics of the graphs as well? Of course, G does it. If you fix the G value of power of G, then there is always a finite number of graphs that you can draw. You could ask the same question. If you fix the power of h bar, then is the diagrammatic expansion also reflects an expansion in h bar? And if that is so, then how does that happen? And the answer is that the number of power of h bar in some way of, if we count it properly, then one sees that the power of h bar is basically the counting of number of loops. For example, this has one loop factor, so it will be h bar to the power 1, and so on. But we have to make a precise statement. Let us now go through the systematics of recovering h bar and classifying terms in terms of power of h bar. So h bar or loop expansion. So first step is to recover h bar for any diagram. And how does one do that? The rule for doing this is that you replace every delta, every propagator, by h bar times delta, and every g by g over h bar. The reason is simply that, recall, the propagator delta x minus y, the expression for the propagator that we got initially was dq over h bar times dq over 2 pi to the power d to the ip dot x minus y divided by q dot x minus y divided by q square plus m square. So therefore, if we had set h bar equal to 1, we were basically dealing with this we had basically dealt with this part. We set this h bar to 1. So to recover it, you just multiply the existing expression, multiply the existing delta by, or delta tilde in momentum space, by a factor of h bar. And in the path integral, the phase that we had is e to the power I by h bar times s. And that basically gives you e to the power I by h bar. Within s, I have the potential V, which has this coupling G. So basically, I have I by h bar times G times expectation. I mean, the integral of phi q. So G always, because G is a coupling which sits in the potential. And in the path integral, we have action divided by h bar. The phase depends on action divided by h bar. Every coupling, not only G, in 5/4, 5 to the any other power, all these couplings will be scaled by 1 over h bar, right? I mean, if I set h bar equal to 0, whatever I see that coupling, when I recover h bar, then the coupling, each time the coupling appears, it appears like G over h bar. Then we define what is called amputated diagrams. That is given by so you have this the endpoint function in momentum space, which is given by this, and as we have seen earlier that that g tilde n has an essential factor of capital P of the external momenta. You basically take out that, and rest is the amputated amplitude. Basically the external momenta are amputated. So this is the amputated diagram. Constituted out of internal lines and vertices. In the internal lines are of two types. There are internal lines which are at the tree level, and there are internal lines which are involved in loops. In the loops, so the two types of momenta, all these momenta are integrated over. Some of them are uniquely fixed by the external momenta, and the loop momenta are integrated over, and the vertex factors. This is what constitute this amputated amplitude in terms of so this is the external lines factor, the factor coming from external lines. So if this diagram G tilde has any particular diagram where we have this P1, P2, P3, and so on, then this is basically the amputated diagram. Now, in this diagram, in this amputated diagram, there will be I. It is given by I and V, where I is the number of internal lines with momentum. So these are given, so they will be having parameterized by the momenta, labeled by the momenta, Q1 to Qi, and V is the number of vertices, and that will give rise to a V number of delta functions, each having a linear function of P's and Q's. So the V, so therefore there are V conditions. So apparently speaking, there are V conditions on internal momenta Q1 to Qi, and those are L1 equal to 0, L2 equal to 0, and so on up to LV equals to 0. However, combining all of them together is equivalent to the overall momentum conservation, and that is independent. of internal momenta, and therefore there are only v minus 1, only v minus 1 of them conditions are independent. This implies that the number of internal momenta that remain unfixed is given by I as the total number of internal momenta minus the number of independent equations constraining them, and that is I minus v plus 1, and that is L. L is the number of loops, because we know from the Feynman rules that we have seen that you know all these delta functions will actually fix the internal momenta q's in terms of the external momenta p's, but all of them cannot be fixed. Whichever will not be fixed, since every internal momentum in this current version of Feynman rules is integrated over the only the internal momenta that will not be fixed by these equations will remain unfixed, and they will be integrated over. And we know that the momentum integral that we have within the Feynman diagram are the ones that are running in the loop. So that is so for each loop there is a momentum that is integrated. So the number of unfixed momentum, non-fixed internal momenta is same as the number of loops of the diagram. So this is a standard result relating loops, internal lines, and vertices. This is a standard result in the graphs or circuit theory. We are basically to prove this is basically the same argument that one gives. We just had gone through that argument. Now, what the usefulness of this argument is that of this result is that this L is a topological property of the diagram. How many loops are there? So if you fix the number n, capital N, the number of external lines, then you could ask what are the diagrams at 3 loops or 4 loops. So number of loops, if you fix the number of loops, it uniquely fixes the number of diagrams that you can draw for a 4-point function with that many loops. So that's a topological property, and this number of relation of that to the number of lines, internal lines and vertices, means that for each internal line we have a propagator which will be scaled like h bar, and for each vertex we have a vertex factor which is scaled by 1 over h bar. So that automatically tells you that this form automatically tells you the h bar power of the diagram, and that means the power of h bar and the loop number of loops are related in this way. Okay, so this is what we will make more precise in the next part.